All right, let's begin for today. As usual, thank you for joining, students. We're going to do the warm-up problem. We're going to go over some new content. And then you're going to have time in your breakout rooms to actually start this coming week's homework. So let's jump right into the warm-up. So you can see there are very similar boxes there. They're being pushed across that floor and the mass, and the net force for each box is given. That's very close readings required here because you have to notice that that's the net force. And they also give you an initial velocity, and then they ask you to determine two things, or I ask you to determine two things: the acceleration of the box, and as well as the final velocity for each box after 2 seconds. So problem one is a fairly straightforward application of Newton's second law, right? Which says that net force equals mass times acceleration. So if I solve for acceleration, all I just really need to do is for each scenario, plug in the net force, which is the F value, divided by its mass, and I'll get an acceleration. So when you do that for every box, and you rank them, you see the following. So notice I just did it up there at the top. You find that A is the highest acceleration, D is second, C is third, and B is last. For part two, with the final velocity, we go back to kinematics, and you just have to use, the easiest way to do it is to use that equation: final velocity equals initial velocity plus the acceleration times the time. I give you the time in number two, it's 2 seconds. So all you need to do is just take that initial velocity, that's 10 meters per second. The time is 2 seconds, and then you just plug in each individual acceleration for each box to figure out what the final velocity is. And I have done that across the bottom there for 2 of them. Let's do the other 2 really quickly here. They would be, let's see, they would be, so we go 10 plus 2 times 3.75. So 3.75, so that would be 17.5 meters per second. And then this would be 10 plus 2 times 6.7. So that's 6.7 times 2, what is that, 13.4. So that would be 23.4 meters per second. I didn't ask you to rank them, so as long as you give me that, that's fine. I see there's something in the chat. Sal asks, could you also just use acceleration as change in velocity or change in time, then add that to the 10 meters per second? Yes, and you actually answered your own question, Sal. That is effectively what I am doing. So another way of thinking about it, absolutely. Okay. Super. So hopefully that was a good trip down memory lane. These are wrong. I did not update the slides, so ignore these. We are going to talk about electromagnetic, the difference between mechanical and electromagnetic waves, but the other 2 we did last week, and we're not going to talk about them this week, unless you have questions, of course, that you can talk to me about in your breakout rooms. We are going to start talking about something called the charge model, and we're going to start talking about something called Coulomb's law. So if I had 2 more learning targets on there, it would be I can describe the charge model, and the other would be that I can apply Coulomb's law to analyze situations. Basically, that's what we're going to be doing. Okay, as you see here, I just want to talk about the guest speakers really quickly, and then we're going to talk about electromagnetic waves, charge model, Coulomb's law, and then you're going to get into your breakout rooms. So also I want you to know, with the new sort of Monday through Thursday schedule, hopefully everyone's aware that teachers, Cleveland staff are not working on Fridays from here on out because of a furlough that was approved by all parties involved. So if you send me an email on Friday, I am not going to respond to it. It's not because I don't want to or I don't like you. It's just because I've been dictated that I really can't do schoolwork on Fridays. So I will get back to you sometime over the weekend if you email me like Thursday night, Friday. You won't get correspondence from me or feedback from me on Fridays. I am available for an all-class flex Thursday from 1 to 2, and other times via remind email, always, except for Fridays, of course. Well, you can send me something, but again, you won't get a response on Friday. This week's science speakers. Tomorrow I am hosting Yuka Sashi. She is doing graduate level work, actually, at UC Boulder / National Institute of Standard Technology. It's an institute called JILA, and she's trying to make microscopes out of X-ray light. So I really hope you join. That date is wrong. Oh my goodness. That had to be rescheduled because of the furlough, and it's actually tomorrow, Wednesday, May 13th at 1 p.m. Okay? So that's when she's talking. I hope you can join. Again, if you're looking for that, it's if you ever forget, it's bit.ly/IBSciSpeak. Okay, that's the document that has the links and everything. All right, and then on Thursday, Miss Ann Bentley, basically, she's looking at sort of nanoparticles and stuff like that. It sounds really awesome. So 2 great speakers lined up again, and I hope you can join for one or both of them. Okay, let's talk about new content. First of all, I want to just talk about a few more things related to electromagnetic waves. I want to make some things very explicit, and then we're going to move on and talk about charge model, etc. But when we talk about electromagnetic waves, I want us to understand that, first of all, in the last few weeks, we've been talking about mechanical waves, waves on a spring, waves on a rope, sound. Those are all mechanical waves, earthquake waves. Okay, but there are another type of waves, which we call electromagnetic waves. And very vital to us, visible light, the light that we can see, the different colors, is the most common example that we can sense with our own sort of innate senses. Okay, but I want you to realize that visible light is really just a tiny fraction of what we call a complete electromagnetic spectrum. And you can see an image here of the electromagnetic spectrum. And there are all sorts of electromagnetic waves that encompass the electromagnetic spectrum. And they include things on the left there, all the way from very long wavelength electromagnetic waves called radio, TV. Someone does not have their microphone muted, so if you could check really quickly, that'd be great. And then as you go to the right, you can see that the wavelengths get shorter and shorter, and we get into things like infrared light, and then from there, ultraviolet light, X-rays, and gamma rays. Gamma rays have really short wavelengths and very high frequency. And the part that our eyes can detect is that really small sliver that I've just highlighted here. This is what we call the visible light spectrum. And you can see there the colors. Some of you may have learned sometime in your past, Roy G. Biv. You can see that played out there, red, orange, yellow, green, blue, indigo, violet, so to speak. And notice that the different colors just correspond to a different wavelength of an electromagnetic wave. So this is something important to realize, that there are these other type of waves, and we're going to talk in the next slide about how they're similar and how they're different from mechanical waves. Okay, so welcome, Stanford. Awesome. Okay, so let's talk about the nature of electromagnetic waves. One thing I alluded to last week, but it's important to realize, is that in free space, meaning in a vacuum, all electromagnetic waves will travel with the same speed. And that is an astoundingly fast speed of 3 × 10⁸ meters per second. That is 30 million meters per second. Or you could think of it as 300,000 football fields every second, roughly, approximately. And we use the special symbol c for the speed of light. And so this wave speed equation that we've talked about already applies also to electromagnetic waves. And instead of saying v equals lambda times f, you'll often see it as expressed as c equals lambda times f, just to indicate that we're talking about the speed of light when we're doing that, the speed of light in a vacuum. All right, so a couple of key points about electromagnetic waves and how they are similar and different from mechanical waves. The first thing you need to realize is that electromagnetic waves are transverse, okay? Remember, mechanical waves can be transverse or longitudinal depending on the type, but electromagnetic waves are transverse waves. And this is an odd thing to kind of comprehend and grasp, and I'm not going to spend a lot of time on it. And it's going to be one of those things that kind of probably puzzles you. That's okay. Electromagnetic waves are these transverse waves where you have an electric field that oscillates in one dimension. And that electric field oscillating in one dimension creates a magnetic field that oscillates in a direction that's perpendicular to the first, to the electric field oscillation. And that magnetic field oscillating causes the electric field to continue to oscillate, and they kind of propagate forward, like you can see there in this drawing, where they are two oscillating fields. And notice the direction of the wave is perpendicular to both the direction of the electric field and the direction of the magnetic field. Okay? So this is one of those things that for purposes of just time and also complex math, can't quite go any further into it now, but it's just a good model to keep in your mind as far as when you think about electromagnetic waves. The more important thing at this point for you to realize is that electromagnetic waves don't need matter to travel through. They can travel through an empty vacuum. And we have an example of that 24/7, 365. That is our sun. Our sun bathes us in electromagnetic waves of all sorts. And thankfully it does that. Otherwise we as humans wouldn't be here. And it travels to us. Those EM waves reach us through the vacuum of space between us and the sun. I do want to make sure you realize that like mechanical waves, electromagnetic waves transport energy from one spot to another. So that is something they hold in common with mechanical waves. They both still transport energy. And again, that's a good thing for us. The sun sends us a lot of energy every day. It's been doing so for a long time. And that's helped the Earth to evolve in the way it has, and for all the species that we talk about, including ourselves, to exist. Okay, so this is the last slide as far as like waves go that I'm going to present to you. We're gonna move on here and start talking about something called the charge model, and we're going to start talking about Coulomb's law. Okay, so let's go. Let's do it. When we talk about charge, things are charged, positive charge, negative charge, okay? Let's go into like chemistry land for a little bit. Some of you have taken chemistry, some of you are taking it right now. Actually, I think all of you have taken chemistry. Or maybe a few of you may be taking it right now. But if we look at a simplified atomic model, you can see there we've got beryllium on the right, hydrogen on the left, and those little grayish dots are those electrons. And the red and the green are the nucleus of the atom, right? And that's where the protons and neutrons are. And so if you can see here, and again, this is just a very simplified model, but sometimes we think of the atom as the electrons sort of orbiting around the nucleus. I know some of you are out there saying, well, Mr. Bob, I've learned recently that's not quite right. And I agree with you. There are inadequacies about this model, but for us today, this works. And so we're going to use it because it works. And again, in science, we make models that work for us to explain situations that we're trying to explain. And this one works for us right now. And so notice each proton, you probably learned somewhere in the past, has a charge of +1. Each electron has a charge of -1. And as long as the number of electrons equals the number of protons, you have a neutral atom, right? In other words, on the right here, if I just do a little math, I have +4 protons. And then I have 4 electrons, so -4, so the net charge is 0. Same thing over here with the hydrogen atom. +1 proton in the middle, -1 electron orbiting it, so 0, total charge is 0, the atom is neutral. But if I take away an electron, you ready for this? Here we go. Here we go. Where's it going to go? When's it going to go? There it goes. If an electron is moved from an atom, then what happens? This charge balance has been interrupted or disrupted. And now I no longer have -4, but it's now -3, which means now I have a +1. I have a positive ion, and the beryllium is positively charged. Okay, a positive net charge because it has more protons in the middle than it has electrons orbiting it. And likewise, if an electron gets added, say, there it comes, do you see it? The electron gets added to the hydrogen atom, let's say, then now I have 2 electrons orbiting the nucleus of the hydrogen atom, and I just have 1 proton still, so that becomes -2, and this becomes a -1, so that would be a negative ion. Okay, so hopefully this is something you've been exposed to before. If not, I'm just doing a brief review for purposes of building upon it. From there, I want to bring us to this idea of what we call the elementary charge, and this is really vital for us in physics. I don't think you talk about this in chemistry so much, but when we say the charge of an electron is -1 or the charge of a proton is +1, or by the way, the charge of a neutron is 0, it's neutral, what we're really saying it has a charge of what we call the elementary charge E. And we say it's elementary because up until recently meaning say the last 50 years, we really thought that that was the most fundamental charge you could have. Like you couldn't have a base unit of charge below what an electron is or what a proton is, okay? And so that got a symbol, the elementary charge E, but in science, in physics certainly, we need to use that and incorporate that into the SI system. So to use that in calculations and equations, we have different units. So the SI unit of charge is what we call the Coulomb. And if you remember, this was one of the, actually, no, it isn't, because the amperes, yeah. Anyway, this is an SI unit. It's called the Coulomb. I was about to say this was one of the 7 fundamental units, but it actually is not, because the ampere is what's defined. But anyway, I digress. So for this slide, for the purpose of this today, what you need to realize is the following. That when we say an electron has a -1 charge or a proton has a +1 charge, that means its elementary charge is 1e, and there's a conversion that's really important, and I would give it to you on the data booklet, but you need to make sure that you can use it, and you're going to get some practice using it. One electron basically has a charge of magnitude 1.60 times 10 to the 19th coulombs. Similarly, the magnitude of the charge on a proton is the same, 1.60 times 10 to the 19th coulombs. The only difference is one is positive and the other is negative, and we're going to see how that plays out here. But this is a really important idea, and an idea we're going to carry forward. Okay, so a simple experiment we can use to demonstrate the creation of charge imbalances, okay? And you've done this before as a kid at some point. You rub a balloon against your hair, against your clothing, whatever. And when you do that, the wool gains positive charge and the balloon gains an excess of negative charge. In other words, some electrons are transferred from the wool to the balloon, okay? And so then if we take 2 balloons that we've done that with and we try and bring them together, we find that they push each other away, okay? The green and orange balloons repel each other. You can see there I've just drawn a very simple free body diagram of the green and the orange balloon when they get in close proximity with each other. And by the way, we're ignoring gravity in these situations. Also, if we try and bring the wool samples close together, you're going to find they repel each other as well. So that's interesting, right? So we can say that like charges repel. In other words, if a positive charge comes closer to a positive charge, each is going to feel a force, a repulsive force, pushing away from the other. And the same thing goes if you get 2 negatively charged objects. Now notice in the balloons and the wool samples, they still have some of the other charge left, but the only thing we're representing here is the excess charge they have. They have more electrons or fewer electrons in the case of the wool, right? So we're just representing the excess charge. The other thing we'll find out is basically if you try and bring the wool back close to the balloon, they actually will attract each other, okay? And so we can say that unlike charges or opposite charges attract each other. And this is really important because this brings us to something called the charge model. This is one of those fundamental ideas in physics, really important. And it basically says this, that if we have 2 negative charges, it's kind of a summary of the last 2 slides. 2 types of charges exist, positive and negative. Like charges repel, and unlike charges attract. Excuse me for a second, I gotta let my dog in. Come on. Okay. So this is a really important fundamental idea, one that you've intuitively understood before, but we're going to use it in much greater detail here. All right, you ready for a joke? Who's ready for a joke? Of course everyone is. Who wouldn't be? Let's do it. All right, the joke. The joke is the following. Hold on, I gotta get something. There it is. Okay. All right. The joke is, why did the bicycle fall over? Why did the bicycle fall over? Why would a bicycle fall over? Because it was too tired. All right. All right. I think someone else contributed to the laugh track too. I like that. Very good. You know what we should do? Let's do this. Yeah, we'll do it next time. Next time we have a joke, I'm not going to do a laugh track, but I'm going to want you all to unmute your mics simultaneously and just laugh, and we'll see what happens. Yeah, that's a great idea. Thank you. All right. Okay, so now I want to talk about something called the conservation of charge. So the conservation of charge says this. It's quite simple. It's like other conservation laws you've probably come across. The law of conservation of charge says that charge can neither be created nor destroyed. But charge, meaning electrons, protons, positive, negative charges, can be transferred from one object to another. But if you take into account all the objects in a system, the total charge of the system has to remain the same. Okay? This is an important idea as well. So we've got charge model, we've got conservation of charge. All right, let's apply it. Let's apply it to a quick sample problem. So here we go. There you see, there's my dog, Dobby. And let's say a dog's fur, like your hair, acts like wool when you rub a balloon on it. A balloon has picked up negative 150 microcoulombs of charge from Dobby. Okay, so I rubbed a balloon against Dobby, and some electrons were transferred onto the balloon from Dobby's fur. So then the question is, how many electrons have been transferred? And then do I have another question? Is B, what is the charge on Dobby? Express your answer in coulombs. All right, let's do this. So letter A says, what do we need to do for letter A? Well, this is a factor label problem, by the way. So if you've been missing factor label, this is your chance. Okay. Now, when I say how many, notice what I'm going to do here is I'm going to ignore the negative sign. We know if it's negative, then the electrons were transferred from the wool to Dobby, or from the fur, excuse me, from the fur to the balloon, Dobby's fur. And it's just a question of how many. So if I have 150 microcoulombs, okay, and I have to get to electrons, I'm going to have to do two conversions here. I'm going to have to go from microcoulombs to coulombs, and I'm going to have to go from coulombs to electrons. Okay, so notice I've set up two conversions there. Now, if you take out your handy-dandy metric conversion, we know that what? It takes 1,000,000, or 1 times 10 to the 6 microcoulombs is 1 coulomb. And then we know from the previous slides that 1.6 times 10 to the negative 19th coulombs is 1 electron. So, oops, let me make that clear, 1.6. Okay, so go ahead and do that on your calculator. I'm going to do it on mine. 150 divided by 1, second function e, 10 to the 6. Divide that again by 1.6, second function e, negative 19. And I get something that is roughly 9. If I'm going to stick with sig figs, I'm going to call it 9.4 times 10 to the 14th electrons. Okay, so that's how many electrons have been transferred, 9.4 times 10 to the 14th. All right, and then part B, what is the charge on Dobby? Well, this is really simply an expression of the law of conservation of charge. So if the balloon has negative 150 microcoulombs of charge, Dobby has to have, similarly, positive 150 microcoulombs. But I expressed the answer in coulombs, so that would be 150 times 10 to the negative 6 coulombs, or if I want to be scientific notation, it would be 1.50 times 10 to the negative 4 coulombs. That would be the way I could write it. Okay, let me pause there and see if anyone has any questions about what I just did. Okay, so you're gonna have problems like this in the homework that you have. Let's go a little further. I'm gonna keep going. If you do have questions, you can still write them in there and I'll come back to them. Let's talk about Coulomb's law. Coulomb's law, really fundamental law here in science, in physics. So French scientist Coulomb, he studied this charge and charges and studied sort of the forces they exert on each other. And he discovered the following, that if I take 2-point charges, Q1 and Q2, and let's say, I'm going to say Q1 is here, I'm going to say Q2 is here, and they're separated by a distance. Let me pick a different color to make it a little more nicer. And let's say the distance between their centers is r, okay? So there we go, we got Q1, we got Q2, 2-point charges separated by distance r. Then the force that each exerts on the other can be calculated using this formula. And here it is. Basically, you take the magnitude of the first charge, magnitude of the second charge, divide it by the distance between their centers squared, and you multiply it by Coulomb's constant, which is that K value. And poof, you have the force between two objects. So let's make sure we understand what each of these are. While we're doing that, oh yeah. While we're doing that, I want you to think about something. Does this remind you of another law we've studied earlier this year? Hopefully it does. So this is charge in coulombs. And this is distance between their centers in meters. Okay. So that's Coulomb's law. And maybe you made the connection, some of you hopefully made the connection, that this looks an awful lot like, yes, Cade, coming through. The law of gravitation, Newton's law of universal gravitation, right? Because if you recall, let's go back, sorry. You recall that law was G m1 m2 over r squared. So notice we replace the masses with charges. Distance is the same, it's an inverse square law. We just have a different constant. Instead of the gravitational constant, we have Coulomb's constant. So scientists for centuries have been amazed and puzzled by this. And this really suggests that, and scientists and physicists for centuries have been trying to kind of unify this, because if these things are similar and the equations are similar, there's got to be some sort of underlying fundamental idea that maybe is beneath all of this, right? But so far we haven't been successful. Haven't been successful in kind of identifying how this works. And there's something called the Standard Model, which has helped unify like electricity with magnetism, but gravity is still kind of hanging out there and still not fully understood, and how it works with, how it kind of fits into the picture of everything else. That could be a fascinating topic to explore sometime in the future if you wanted to on your own. Okay, so now let's get to the demonstrations. Hopefully you all saw the 5-minute video. If you did not, that I put together with those 3 demonstrations, the tin can, the meter stick on the mouse, and the paper dots. Please go ahead and make sure you see those at some point. And the question I want to walk through with you here is, how can you use our charge model and Coulomb's law to explain the observation of the demo where the glass rod moved the wooden meter stick without touching it? Okay. Typically, I find that students can predict what's going to happen with metal objects, but they get very surprised. And like I said in the video, I was very surprised when I first saw this wooden meter stick demonstration. And so I want to talk through how this happens. Okay, so let's think about something here. Let's think about, we have this meter stick, right? Here's the meter stick, okay? And the meter stick is what we say neutrally charged at the start, right? So at the start, the meter stick has, and I'm going to basically exaggerate things here, but you know, it's got plus, minus, plus, minus, plus, minus, evenly distributed, right, on both ends. You can think of the meter stick as starting out this way, okay? And then I take that rod, and what did I do with the plexiglass rod? The first thing, pretty much before every demonstration, is I rubbed it. I rubbed it with that cloth, right? And rubbing it with the cloth, what happens is it gives excess electrons. And I'm just going to show the excess charge here. Okay, so there's the rod with the excess charge. So what happens? Now, oftentimes students think, and again, this is something that I thought too originally, when you bring it close to something that doesn't conduct electricity, nothing's going to happen. Like, so you bring the rod close to a tin can. Hey, that makes sense. It's metal. Metal conducts electricity. the tin can's going to move. But why would it move a meter stick? Well, let's think through this. You are right in saying that the meter stick cannot, the electrons in the meter stick maybe are not as free to move about as, say, the electrons in the tin can. But if I bring this close enough, this rod close enough, okay, and now I'm going to exaggerate this effect here to give you a sense for what's going on here. What is going to happen inside the meter stick is basically, if I'm a positive charge, remember, like charges attract, right? So the positive charges are going to slightly move, and again, I'm exaggerating the effect here for purposes of this illustration, but you can imagine that in that meter stick, the positive charges are going to move slightly more towards it, but more importantly, and actually physically what's happening, is those electrons that are revolving the nucleus of the atoms, those electrons are going to just move a little further away from all that negative charge that's on the rod. So notice, on average, what I've drawn down there is that the electrons are further away from the rod, and the positive charges, on average, are closer to that negative rod. Now, Coulomb's law says what? It says that the force equals K Q1 Q2 over R squared. So notice my R values here, and I'll try and use two different colors. Notice that the average distance here to the protons, I'm going to call that R1, okay? And then the average distance to the electrons, I'm going to call R2. And what do we notice? We notice that R2 is greater than R1, right? So even though I have the same amount of positive negative charges still on the meter stick, the distance that those charges are to the excess negative charge on the rod is different now. And so how does that manifest itself? In Coulomb's law, if I look up here, right? Remember, let's write this here. As the distance, the average distance goes up, what happens? The force goes down. So if I draw a free body diagram of the meter stick, on the meter stick, then what am I going to see? Well, I'm going to see the following. Because these negative charges are further away, then they are going to exert a force. There's a repulsive force, right? So I could represent that with this red arrow, and I could call that F2, right? The repulsive force that you get from those negative charges being close to those other negative charges. But how does that force compare to the attractive force that the positive charges are going to feel from that negative charge? Well, the attractive force is going to be bigger. Why? Because they're closer. So if I draw this arrow, this is going to have a larger arrow, right? And this is F1. So since F1 is greater than F2, there's going to be a net force toward the rod. And that's what you saw in the demonstration, right? You saw me be able to move the glass rod. The glass rod basically attracted the meter stick to it, and it didn't matter which direction. When I switched direction and put it on the other direction, the meter stick would slow down and it would change direction. It was always being attracted to the rod. And now you see why. And you see why using the charge model and using also the idea of Coulomb's law. Isn't that neat? Hopefully someone out there is smiling or has goosebumps or something. And let's talk about the paper dots really quickly, because I think that's another good one. I don't know that I have enough space here to do it. I'll just kind of carve something out here on the bottom here. So paper dots is really cool because with the paper dots also, you have, here's the rod. It's the same idea. The paper dot initially gets attracted to the rod, right? Because of the same idea as the meter stick. But in this case, the paper dot actually comes into contact with the rod, right? Because it jumps up. And so the cool thing is what happens, and I'll try and zoom in here, and I'm going to try and do my best here. I don't know how well I'll do. When this happens, then you actually get a jumping of negative charges from the rod over to the paper dot, okay? So in a matter of a split second, or maybe a second most, what you saw is you saw the paper dots would come up, and they would go back down, up and down. And what's happening is, at first they're attracted because, like we talked about the meter stick, but as soon as some electrons get jumped on or jump over to the paper dot, then you have negative, excess negative, and excess negative. You get a repulsive force, and so the paper dot kind of falls back down, or I should say gets repelled back down onto the table. And sometimes this can happen a couple times, or you can see it with a couple different paper dots, until basically the charge is neutralized, so to speak. You get the same amount of charge being deposited on the paper dots, on the tabletop as well, because there's transfer of charge there. There's also, by the way, transfer of charge into the air because the air has water molecules. And so over time, those effects kind of go away. But it's kind of cool for those couple of seconds, right, where you see the paper dots kind of dancing up and down, and then now you can see why. All right, very good. All right, we're getting close here to, let's do just some calculations. I do want to do one more sample problem, or two more sample problems actually, then you're going to get breakout rooms. But I just want to show you how to use Coulomb's law in a calculational problem. So let's say here we've got, this is practice problem number 1. Find the Coulomb force between a positive 5.0 millicoulomb point charge and a negative 3.0 millicoulomb point charge located 4 centimeters apart. 2, draw the force vector that each charge feels due to this electric charge. Let's do number 2 first, actually. The force vector, let's say I have positive charge on the left, negative charge on the right. So what's going to happen? These are going to attract, right? So this one, I can show a force here, and I'm going to show a force here. Now, question, how big should I make these force vectors? Should one be bigger than the other? Sometimes I hear students say, well, the 3 millicoulomb force that it feels is going to be bigger because it's feeling it from the 5 millicoulomb charge. Well, but remember, Newton's third law says what? Forces come in pairs, right? Object A exerts a force on object B of a certain amount. B exerts the same force back on A. So these are actually, and I'm trying to make them, these are actually the same size. They should be. Okay? The other thing I want to point out is that Coulomb's law does not tell you the direction of the force. Sometimes students type in, write in a negative and a positive, and they think they get a negative number for a force, and they're like, wait, what does a negative force mean? Don't use Coulomb's law to figure out the direction of the force. Use drawings and your understanding of the charge model to figure out the direction of the force. Coulomb's law just tells you the size of the force. Okay, so here we go. F equals K, Q1, Q2 over R squared. And this is really just kind of a plug and chug, and you just have to keep track of your metric prefixes, et cetera, et cetera. So we know K is 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. You don't have to put the units in there if you don't want to. The first charge is 5 millicoulombs, so milli is 10 to the negative 3 coulombs. The second charge is 3 millicoulombs, so that's 3 times 10 to the negative 3 coulombs. And then the distance between them is 4 centimeters. I have to convert that to meters, so 0.04 meters squared. By the way, that's one of the most common mistakes I see students make. They don't convert from centimeters to meters, or they don't put all these in the correct order. And then the other common mistake I see students do is they don't square the bottom. Okay, so go ahead and take 30 seconds here in your calculator. Let's calculate this. I'm going to do the same. Okay, get a big number here. I get 8.4 times 10 to the 7th newtons. I could have done something wrong, so please double check me. Okay. So big number, and just so you know, electric force much stronger, generally speaking, than the gravitational force. One example is probably right now, all of you are sitting right on a surface of some sort, a chair, a floor, a bed. So am I. And the only reason that I don't fall through that chair, because remember, there's a lot of empty space in atoms, is because the electromagnetic force between the electrons on the surface of the chair and the electrons on the outside of my jeans, so to speak, they are counteracting that gravitational force that's pulling me towards the center of the Earth. Something interesting to think about. Okay, so let me see if there are any questions. Yes, and Sal asked the question, what happened to the -3? And so let me just be very explicit about this. When you put your charges in Coulomb's law, always put them in as positive numbers. Because again, all we're doing with Coulomb's law is figuring out the size of the force. And then you're going to look to your drawing and the charge model that we've talked about to figure out the direction of the forces. Okay? So yes, if you have negative charges, put them in as positives in Coulomb's law. Okay, so one more I want to do here, and then you're going to get time in the breakout rooms. Here's another problem. The Coulombic force between 2-point charges shown above is calculated to be 56 newtons. Determine the new Coulombic force, that means Coulomb's law force, if the distance between the charges is doubled and the right-hand charge is cut in half. So notice in this situation, this is what we call comparative scenario analysis. I don't give you numbers. I don't give you the size of the charges. I don't give you the distance between them. But I give you enough information to do what we call comparative scenario analysis. So let's go through this. We know that in the original scenario, F1, K, Q1, Q2 over R squared, right? And in this case, Q1 is Q, Q2 is 2Q, and the R is L, so L squared. So we know, let's just kind of clean this up. 2K Q squared L squared equals a force, and we know that's 56 newtons. Pause there. All I did there was I just substituted in what the problem gave me for Q1, Q2, and the distance. Okay. Now, the new situation, what do we know? The distance between the charges is doubled. So L becomes 2L, and we know 2Q becomes cut in half, so that becomes Q. So how does that change our situation here? So we know now that F2 equals K. Q1 is still Q, but then the second charge is now become Q, and the L has become 2L squared. Okay? All right, now here's the key about these sorts of problems. What you want to do is you want to get back to something that you can plug in for this. So I want to get 2K Q squared over L squared in my equation below. So let's see how I can do that. So what I'm going to do here is F2 is going to be, so let's see, I have K Q squared. When I square the L and the 2 on the bottom, I get 4L squared. Okay? All right, so how can I get a 2 on the top? Well, why don't I just multiply both top and bottom by 2 over 2? And if I do that, notice what I get is I get 2KQ squared and over L squared. And on the bottom I have out here in front, by the way, I'm going to leave this like this, and this is 4 times 2. All right, just quite a bit there, and I want to kind of talk through that a little bit. Again, I'm just trying to get what I see in purple brackets down here also in purple brackets. So to do that, I multiplied top and bottom of the right-hand side by 2. And that allowed me on top to get 2KQ squared. I kept the L squared in the purple brackets, and I brought out in front the 4 that was already in the denominator, and also the 2 that I multiplied it by. So notice what I get here is this is 1/8 what's in the purple brackets. And we know the purple brackets is equal to 56 newtons. So my end result here is that the new force is basically 1/8 what the original force was. 1/8 times 56 newtons, or 7 newtons. So notice I was able to figure out the new Coulombic force without actually knowing the charge and actually knowing the distance, but just knowing a relationship between how it originally was and how it changed. Again, we've done this before. This is just another example of comparative scenario analysis. Big thing in IB, also big thing in AP. Also big thing in colleges. Okay, I am going to, I think, yes. So we're done with the material, and now it's a chance for you to work in your breakout room. So let's make sure we understand what the assignments are for this coming week. So you have 2 assignments for this coming week. Problem set 8-1 and electric fields reading assignment. And let me be clear, this one is due Friday night, the first one, the problem set. And this one is due Monday morning, and it's Monday morning before class. I basically want you to do the second one, the second assignment, before you come to class next week, next Tuesday. Actually, I should make it Tuesday morning. Let me think about that, okay? As I have said it right now, Google Classroom, the first one's due Friday night. Yeah, we'll make this due Tuesday. Actually, we're gonna make it due Monday night, because Monday night and Tuesday morning are the same thing, because you guys roll out of bed and just roll into this class. So do Monday night. I'll be changing that. Okay, so so the first one is a problem set, and the second one is a reading assignment where I want you to answer some questions after you do the reading. The problem set, you're actually going to start that now in your breakout rooms. And what you're going to do is, as you've done before, you're going to go to your breakout room. I'm going to give you that breakout document here in a second. I'm going to be depositing a Jamboard in the breakout room. Remember, the Jamboard is like the common whiteboard you can use. And so I want one person to present the whiteboard as you would be presenting a document or something, but all of you are going to be able to contribute to it. And so what you're going to do is you're going to pull up problem set 8-1, and you're going to work with your table mates, your breakout room mates, so to speak, working through the first few problems, okay? And here's what I'd like you to do. I believe like problem 1 and problem 2, there's 1A, 1B. Instead of doing 1A and 1B, do 1A and then leave 1B off to the side for you to do on your own. And then do 2A and leave 2B off to the side for you to do on your own. Because I'm going to allow you to do up to 3 parts of problems on your Jamboard. And if you do that, you don't have to do them in your actual assignment that you turn in individually. So what you do together as a group counts towards your individual assignment, if that makes sense. Similar to what we've done in class before. Okay, so unless there are questions, a couple more things. I said start problem set 8-1, use a Jamboard to complete up to 3 in-class problems as a group. Be sure to share your work, including factor label methods for conversion. I would like you to rotate who writes. I know that writing on the Jamboard can be weird because you're using a mouse sometimes or your finger. Just do your best, and you'll get better with time. And again, any problems you complete on the Jamboard, you don't need to complete on your own. Okay. If there are no questions, if you have a question, write it in the chat box in the next 30 seconds or so. While you're doing that, I'm going to get the breakout room document, put it in there, and then have you go to the breakout rooms. As usual, if you find there's no one, like look ahead before you go to a breakout room. If you know there's no one there from your breakout room, or no one in this session right now that's going to be in your breakout room, then just pick another breakout room you feel you can work well in, as usual. Okay, there's the document. I will hang out for about another minute here just to see if anyone has any individual questions. But again, I will also be visiting the breakout rooms, and you'll have a chance to dialogue with me in the breakout rooms. Okay, thank you, everyone. This concludes the big session for today.